Okay, so now a big official welcome from my side. I'm happy to see that we have such a good participant number for the second day of our Gracious Final Stakeholder event yesterday. And I hope you had, many of you had the chance to attend yesterday's meeting. And we had a training session where you could learn a lot about the framework and the different yatas and a lot of other things that is discussed. Today, we will focus on case studies that have been conducted during the project. Some of them were internal, some of them were external, and we selected a good panel of them for you. And we will have the possibility to discuss some of them during the event. But before we will start, I will now share again the link in the chat. So we prepared a little survey on mentimeter.com. So you just go to www.menti.com and there is a survey consisting of 2 questions. Currently, the first question is open. Yeah, you just need to type in the code. And the first question is asking you from which country are you joining the event? And then we will let that open for a while. And then I will switch to the second question concerning your scientific background. So please, if you would like, just let us know from where are you joining the event. And I can have a little look. It's already coming up very nicely. So this gives me the opportunity to also welcome our speakers of today's event. I have seen most of them are already in. And I have the pleasure now to open the meeting with a couple of few introductory slides that I'm happy to share now. So now you should see my screen and to provide you a little background on what you can expect today. So yesterday, you heard a lot about the Gracious framework that has been developed. Vicky nicely presented that, but just as a quick reminder, so the Gracious framework is depicted on the right-hand side. This is the framework in a nutshell. So we have an entry point to the framework, to the grouping framework, where users can make a decision whether they would like to start with a single nanoform only, or maybe they already have a provisional group of nanoforms in mind. After that, there is a basic information step, which will then guide you to the formulation of initial grouping hypotheses. And here, Gracious has developed a couple of predefined grouping hypotheses that might be applicable for the specific user case. In case the predefined hypothesis would not work for your case, you also have the possibility to formulate an own grouping hypothesis. And Gracious has developed a template that guides you how to formulate your own grouping hypothesis. After that, this is then where, let's say, the magic will happen. No, not the magic. So this is the detailed assessment step. So Gracious has put together a whole bunch of different yatas, integrated approaches to testing and assessment that guide the user through selection of relevant decision nodes relevant for the specific grouping hypothesis. And behind each decision node, there is a testing strategy proposed consisting of 3 different tiers, having very simple assays in the first tier up to, let's say, in vivo tests that are suggested for the 3rd tier. And this yatas help the user to construct a data matrix, and based on the data matrix, a grouping decision can then be made. So this is the guidance in a nutshell that also has been explained yesterday. It's pretty much aligned with the ECHA guidance that is relevant for regulatory grouping in Europe under REACH. So you see here an overview of what has been established in Gracious. In total, 17 human health related yatas have been put together. 6 of them cover the inhalation route, 7 the oral route for the dermal route. And then on the environmental side, we have 20 yatas, 10 of them focus on dissolution, 7 on aquatic toxicity, and 3 are for effects in soil. And then quite a whole number of these yatas have been tested in grouping case studies. In total, we had 8 internal case studies ongoing, but also we had 6 external case studies. Most of them have been testing a complete yata and a few of them an individual decision node. So this is just an overview on the internal case studies that have been conducted, and those that are highlighted in green, we will have the possibility to discuss today during this meeting. However, we will provide a recorded version of the others shortly after the meeting. So also you will have the chance to learn more on the other case studies. Yeah, you see quite many of them are on the inhalation side, one is on the oral side, and 3 are environmental. And this simply had to do with the fact that we also needed to consider data availability. And so, of course, a lot of data is available for inhalation, but nevertheless, it also is a very relevant route of exposure. This slide finally also lets you know about which external case studies were conducted. Luckily, we were approached by different stakeholders in a stakeholder consultation that we have conducted, and those expressed their interest to run an own case study, of course, with the support from Gracious, providing the IATAs and other expert advice. And today we will have the possibility to hear at least 2 of them, one conducted by NIOSH and the other one by Arche Consultancy together with the International Sync Association. So that makes us very happy and very proud. And before we now start with the first session, please let me remind you about a few housekeeping rules. So it would be good if you can already indicate your questions in the chat while the talks are ongoing. And we have support here. Vicky, for instance, will have a look at the chat. And based on the chat, we will also select the questions then for the overall discussions that we have planned after each session. But also we have the final overall panel discussion in the very end. So we will select then questions from the chat for these discussion rounds. And of course, during the discussion, you also have the possibility to directly raise a question. Just raise your hand. So it would be good to raise your hand so we can identify who is speaking. Also, it would be nice if you can briefly say who you are, then of course ask your question. And in between, while you are not asking a question or presenting, please keep your microphone and your audio muted. Okay, just before we begin, I would like to share with you the outcome of the first Mentimeter. From which country are you joining the event? Obviously, Germany is quite well populated, followed by the Netherlands, Belgium. But you see, we have a couple of different countries, even Japan and the USA. And so I think this gives a good reflection. If you like, you can still give your vote here. Just go on www.menti.com and use this code. And I will open now the second question for voting. Just let us know from which type of institution are you, is your background. So is it academic institution, university, regulatory agency, large company, maybe also small company, private business, or any other that I may have forgotten. And you see now live how the polls are coming in, just to give us a flavor who is our audience. And then we are directly going to our first scientific session. It's really good to see. So I think also in terms of your background, it's quite well spread. Yeah, I think we don't have to wait for the very last voices coming in. So I think we are quite well populated and we should stay in time. That's why I will finish now this introductory part, and I'm happy to lead over to the first scientific session where 2 case studies will be presented. Both of them deal with fibrous materials, so HAN, high aspect ratio nanomaterials, and human health and inhalation. The first talk will be given by Fiona. It's an internal Gracious case study that will be followed by an external case study conducted by our colleagues from US NIOSH. And then we will have a common discussion at the end of both talks. Yeah, so if you have questions in between, please type them in the chat all the time. And yeah, we will follow the chat. Fiona, are you? Yeah, I see already Fiona is sharing. Okay, so Fiona, the floor is yours.
Thank you, Andrea. So hopefully you can see this as a slideshow. So my name is Fiona Murphy and I'm based at Heriot-Watt University. I'm just going to give an overview of our internal case study, which was to test the application of the GRACIOS framework for grouping multi-wall carbon nanotubes by similar inhalation, fate or hazard. So with this case study, when we entered the framework, we defined the context as the occupational exposure to multi-wall carbon nanotubes. And the potential for aerosolization of carbon nanotube powder during the production process led us to select the selection of the predefined hypothesis, which were related to the inhalation route of exposure. So the framework also requests classification of the nanoform shape as part of the basic information. So the identification of elongated structures, an aspect ratio greater than 3 of the carbon nanotube has selected the Harn hypothesis as the most relevant GRACIOS predefined hypothesis for grouping these target nanoforms. So we have two hypotheses defined within the GRACIOS framework for respirable biopersistent rigid Harn, which state that following inhalation exposure, long-term pulmonary retention of the Harn can result in lung toxicity, or also following inhalation exposure, there may be a potential to translocate to the pleural cavity where mesothelioma development may occur. So as a Harn grouping hypothesis, we're based on the structure-activity relationship governing asbestos carcinogenicity. The IATA prompts the user to address questions regarding the deposition, biopersistence, morphology, and inflammatory potential of the Harn in order to support a grouping outcome. So this image is an overview of the Harn IATA decision tree, but you can find the full details of this in our Nano Impact publication, which came out earlier this year, if you want to see it in more detail. The specific objectives of this case study were to determine whether this panel of multi-wall carbon nanotubes could be grouped based on a common fate or hazard potential. It was a literature-based study, so we wanted to know if sufficient data existed in the literature to support a scientifically justified grouping. And we also wanted to look at if any of the candidate nanoforms have been excluded from the group and to try and understand at what point and why, and then also how would these nanoforms be treated following on from rejection of this hypothesis. Then more generally, we also wanted to use this case study to evaluate whether the Harn IATA needed any refinement or clarifications. So the panel of carbon nanotubes that we selected for the case study there's 15 in total, and they've been taken from multiple studies that were conducted fairly recently over the last few years at the NRCWE in Copenhagen. We also noted that hazard data from OECD test guideline inhalation studies exists for 5 of these multi-wall carbon nanotubes included in the panel. And this suggests the potential to use these nanoforms as potential source materials if we wanted to proceed to read across after grouping to fill some hazard data gaps. So the relevant data was collected from these published studies and applied to the IATA decision node questions. And this slide gives an overview of the directly available data which was extracted from the NRCWE studies at each decision node and at each tier of testing. But due to the number of data gaps identified in this sort of in-house data set, which is highlighted here in the text in orange, further tier 1, 2, and 3 data was sought from the literature to strengthen the justification of group formation and the assessment of similarity for these nanoforms. So this was done with a targeted literature search, which was restricted to the specific carbon nanotubes that were included in this panel and focused on filling these identified data gaps. Then any information that was found relevant to each of these decision nodes was integrated across the IATA in using the same IATA data matrix. So our initial outcome was that only 2 of the nanoforms NM401 and NRCWE006, which is also known as Mitsui 7, met the criteria for length and rigidity defined by the IATA testing these two hypotheses. Whereas evidence from additional studies then bolstered this grouping by providing some missing information related to the potential for deposition in the distal lung, biopersistence in the lung tissue, and activation of frustrated phagocytosis by both of these carbon nanotubes. And this supported the acceptance of the grouping hypothesis for these two nanoforms. Our next step would be to conduct a similarity assessment between NM401 and NRCWE006 to support read across. For this, we'd like to complete a full size distribution or obtain full size distribution profiles for both the diameter and length of these nanoforms, as it's been shown that you get better segregation or grouping of different carbon nanotubes when a size distribution profile is used. We'd also like to conduct a comparison of the available toxicity hazard endpoints, which include in vitro cytotoxicity data in a number of cell lines, and then also some cytokine expression and cytokine release data. And a qualitative similarity assessment between these two nanoforms, based mostly on expert opinion, is actually currently near completion. However, for 13 out of the 15 carbon nanotubes included in this panel, the hypothesis was rejected, and this is due to insufficient length or rigidity. So these carbon nanotubes should not be included in a group based on a common fate or hazard potential, which is dictated by fiber morphology. So we next considered what would you do, or how would these nanoforms be treated now? I would suggest that you could follow an IATA that is testing an alternative grouping hypothesis. So we also have more general grouping hypothesis for the inhalation route of exposure, which is not specific to fiber morphology. And we would suggest that you follow the IATA for the hypothesis related to respirable nanoforms with very slow dissolution rate. And this states that following chronic inhalation exposure, accumulation of these nanoforms in the lungs can lead to long-term toxicity. So this IATA is supported by grouping based on similar dissolution, reactivity, and inflammatory potential. And this image has been taken of the tiered testing strategy from a publication which just came out in the summer, which describes this IATA in much more detail. Through the case study, we have already addressed the question of dissolution and biopersistence, as this was covered in the HARN IATA as well, and concluded that these carbon nanotubes can be considered slowly dissolving or effectively biopersistent. So therefore, the next step would be to gather data for this panel based on reactivity and their inflammatory potential, and then assess similarity to support grouping of some or all of the remaining 13 carbon nanotubes. So that was an overview of the how we conducted the case study and our initial outcomes. But then we also identified the potential need for refinement of the HARN IATA based on this case study. So first of all, we identified that the some user guidance could be improved. For example, we need to better highlight the importance of the metric used to express length, as different metrics can result in different outcomes, as we see here. So this has been clarified in the guidance document, where we now include more explicit statements related to the need to use a size distribution profile as a summary metric is not sufficient to meet the decision node criteria or to assess similarity for this decision node. We also recognize that carbon nanotubes more often present as agglomerated structures rather than individual fibers. I wanted to think about how this is reflected in the IATA to better enable the user to answer the question or answer the decision node related to the question of, is the HARN rigid and maintain a fiber-like morphology? So our suggestion is that now is the recommendation to include low power, low magnification electron microscopy images, which are representative of the agglomeration state or assembly structure of the carbon nanotubes. And we've proposed that this agglomeration state can be broadly categorized by user judgment into generic bins to decide whether the Harn presents as fibrous, with a fibrous needle-like morphology, or more as granular agglomerates. So this just shows some of our suggested categorization. So individual fibers or line bundles might both meet the criteria of WHO fibers at the constituent Harn or individual Harn level, or the agglomerate level respectively. Whereas granular agglomerates will be defined as agglomerates which clearly do not present a fibrous morphology, and that their aspect ratio of the agglomerates is less than 3. There was a slightly more ambiguous group we've included, which are referred to as tangled fibrous bundles. So these may be agglomerates where the aspect ratio itself might be less than 3, but there's clearly protruding or loosely agglomerated fibers associated with them. And in this context, we would need to consider the potential for release of a Harn or a high aspect ratio structure that would meet the WHO criteria from these agglomerates, or how they in general interact with cells when there's fibrous forms protruding from the agglomerates. I would suggest that if you wanted to take a conservative view, you would answer yes to this decision node, that they do present some sort of fibrous rigid structure, and then proceed to the hazard decision nodes to further support your grouping. And we finally, we also identify the need to more explicitly set out how to proceed through a similarity assessment once you have established your preliminary group. I believe this is actually largely relevant across all of our IATA. So we included an additional directive decision node after the acceptance of grouping as a respirable biopersistent rigid Harn, which prompts the user to construct a data matrix for the target and source material for all basic information, and also all of the IATA questions. And then this will form the basis of your similarity assessment. We also propose that to further strengthen the mechanistic underpinning of the group, further assessment of the similarity in hazard outcomes between the group members should be carried out, and propose that this could be based on assessment of reactivity, inflammatory potential, and or genotoxicity. This could lead to the conclusion that the Harn are either sufficiently similar to support read across, or that read across may not be possible, and that each of these Harns should be treated and assessed individually. So that was just an overview of some of the results and the lessons learned from our own internal case study. But we do recognize that further refinement to the Harn IATA from other external case studies and from feedback from the stakeholder events can also be incorporated into further refinement of the Harn IATA if it's needed. So thank you very much. And if you have any questions, I'm happy to answer them.
Thank you, Fiona, for this wonderful presentation and this excellent talk. Please, everybody, don't forget to ask your questions in the chat directly already now. We now directly hand over to Aaron Erderly from US NIOSH, one of our external stakeholders who kindly agreed to run an own case study. And we are now very curious to learn about the outcome of that. Before we will then have a common panel discussion with Aaron and Fiona together. Okay, Aaron, the floor is yours.
All right, thank you very much. I'm Aaron Erdley from NIOSH, Morgantown, West Virginia, and we're more than happy to be part of this exercise and provide our insight as an external case study. I think what you're going to find that our work represents a really good complement to what Fiona just presented, and we're going to be able to extend some of those findings because we were working with some materials that have a longer length and greater diameter, including the carbon nanofibers. So we've been working with carbon nanotubes for years, all the way from characterization to acellular, in vitro, in vivo, and we've recently completed our cross-sectional human health studies evaluating over 100 workers at 12 different facilities. So we've really been interested, going all the way from the as-produced material, how people are handling it, and really getting an industry perspective. And one of the things we found with the industry perspective was we were always being told not all carbon nanotubes are the same. And we really didn't disagree with that. What we found was that there was this wide distribution of materials within this class or family. And a lot of the work had originally been done on the Mitsui 7, or what we have in our study is MW number 5, or our benchmark material. And companies were letting us know, hey, our material doesn't look like that. Are we going to have the same toxicity, or are we not? So in the same vein of what Fiona presented, we did a study with 9 different materials, 7 multi-walls and 2 carbon nanofibers, where we looked at different endpoints of inflammation, translocation, genotoxicity, and pathology of these different materials. And as you work your way through this image, you can see, here, let me bring up a pointer here. You can see as you go from multi-walled number 1, these are your smaller, more agglomerated materials, up to these larger multi-walled and carbon nanofiber, you really begin to see the transition from agglomeration to a more fibrous material. Now, we did a lot of physicochemical characterization, all of the standard stuff that you'll see in the literature, from diameter to length, surface area, density, all those things. But what I really want to focus on is the 2 aspects that Fiona mentioned, which are needed for really developing this characterization of materials and how we can classify them. And those are sort of these dimensional profiles of the physical dimensions of the materials, being length and diameter. Fiona really clearly illustrated how the means are insufficient. So we were working independently and also arriving at those same conclusions. So not to overwhelm with data, but just focus yourself here on multi-walled number 1. And this is looking at the diameter. You can see that these materials are really focused into really these very 2 small diameter bins. But as you move your way down towards the larger materials, especially this multi-walled 7 here, you can see this dimensional profile start to extend itself. So we have a population of greater diameters. It's not the largest fraction of the population of nominal tubes, but it's still present. And the same goes with length. If you look at multi-walled number 1, very small, pretty much all the materials are in this smaller length of initial bin. But when you look at multi-walled number 7, yes, the majority of materials have this population of a smaller length. But then we also have this wide distribution of longer materials. So we wanted, when we did our analysis using computational modeling with toxicity outcomes, we really wanted to try and capture what impact these longer lengths were having. The second aspect that Fiona really mentioned was this bundling of the materials and the agglomeration. And we really have been working with this over the years in our collaborations with Matt Daum, who's probably been to more carbon nanotube facilities than anybody in the world. When he put this together, this is a sampling of the 12 facilities from our human health effects studies. Only 5% of the material collected in personal breathing zones were in singlets. That means 95% of what was reaching the personal breathing zone was in an agglomerated structure somehow. So when we did our toxicity studies, whether it be in vivo or in vitro, we wanted to do our best to try to replicate this agglomeration pattern. Right here, these are from the personal breathing zones of the workers. And this is what we were able to produce in our laboratory setting. So we feel like we were really mimicking what was happening in the exposure to the workers. This is a very large agglomerated material. This is a very small one with a scale bar here of only 500 nanometers. And you can see these very small, tight agglomerates. We were really able to reproduce this in our exposure scenario. So when you look in vivo, these materials can very easily be taken up by cells. This material, much too large for that process to happen. So when we did this exercise, we had to come up with a matrix and sort of define a exposure parameter. So we really did the cutoff that was used in the field, whether or not we exceeded a 3-to-1 length to diameter ratio. And we found for these smaller multi-wall that the majority of these materials fit into a spherical agglomerate category. But when we got to multi-wall number 4, there was a very abrupt shift to elongated bundles that exceeded our spherical agglomerate dimensions. So all of these materials proceeding to the right here were all in elongated bundled agglomerates. So I'm not going to spend much time on this study, but I think our inclusion is an external case study. We were doing complementary in vivo and in vitro work with this dimensional characterization. We really had a lot of data to contribute to these different decision nodes through this tiered testing strategy. So to put it all together in a single slide, here are our 9 materials. Again, this is multi-walled number 5. So this is the traditional Mitsui 7 that a lot of people have studied. And we really just gave the decision nodes and the outcomes a yes or a no. When you look at these original dimensional physical characteristics, really these smaller materials did not meet the fiber length paradigm or the 10% threshold of length, as I showed you with the red bars of the very small multi-walled number 1, and the 10% threshold that Fiona had mentioned. These materials did not exceed a reason to go forward in the HARN-IATA. So these materials were being kicked out basically on their physical dimensions alone. But if you look at the multi-walled 5, 6, and 7, the larger ones, and the carbon nanofiber 1 and 2, these materials did meet the criteria to move forward. So we had complementary in vitro and in vivo studies. Interestingly, every material was able to induce in vitro genotoxicity, and we didn't see a significant difference between the groups. Okay, so that's something to point out when we're separating, say, pulmonary cancer versus mesothelioma, which is this specific HARN-IATA. So even though these materials, these multi-wall 1 through 4 were sort of kicked out early out of the IATA by not meeting the dimensional characteristics, we still followed them through because we had all of the data. And the dimensional characteristics were really represented in our in vivo findings. Did they induce inflammation? Yes. Did they induce inflammasome induction? Yes. But if we use the criteria in reference to Mitsui 5, it was markedly less of effect here, which would also put them into the no category in terms of the final outcome. Down here, all of these materials that meant the dimensional characteristics, the physical characteristics, we also saw a lot of yeses going across the board here. Now, this last one I want to point out, maybe just to illustrate a point, that as we've gone through our modeling of the physicochemical characteristics with the toxicity endpoints, this one came up with a few no's. And we gave it an uncertain yes because it reaches the physical dimension categories. But what we found was that it takes a combination of diameter and length in these distributions to get the full picture, because carbon nanofiber 2 has roughly the same diameter as carbon nanofiber 1, but it has a dramatically shorter length than carbon nanofiber 1. So when we got to some pulmonary pathology, we didn't see the same pulmonary pathology because it didn't have the length, despite having 100 nanometer diameter. So that's just something to point out. We did move forward. We had some other materials. So how much confidence would we have regarding other materials? And we looked at boron nitride nanotubes. Again, these are our facility images, and this is what we were able to produce in the laboratory. And very quickly, the boron nitride nanotubes were eliminated from the IATA because we didn't get a length, even when we looked at a distribution that was really greater than 2 microns in length. So these are pretty small length materials with a smaller diameter. So here we would have already taken them out of the Harn IATA for mesothelioma. And when we follow them through, we really see no pathology in these animals in vivo. One more point I have on here too is we also had data for silver nanowires. I believe Jenny's on the call here. She did those studies, and even though they had a longer length, I think one of the really good categories to have in here is the dissolution, because the silver nanowires do dissolve over time. So the length becomes less of a factor. So this dissolution category, while these would be yes for some of the silver nanowires that we looked at, the dissolution would be no, moving us to a different IATA as well. So one of the challenges that Andrea asked was, what did we learn? Applications, some constructive feedback. This is sort of the bullet points that Jenny, Vamsi, and myself put together when we were going through this from our end. And we really think the Harn IATA represents a useful extension of our work as well. From an industry perspective, we always heard that the carbon nanotubes and nanofibers aren't all the same. And the way the IATA is constructed, it really illustrates that. I think with the purpose being the regulatory, the safer by design, the precautionary, we were independently arriving at very similar conclusions of how we can group these materials and what we can say about each of them. As Fiona mentioned, and I think I illustrated pretty well here, and you can find from our publications and our ones that are under review now, that profiles of the physical dimensions are necessary. The means only we found pretty quickly to be insufficient to separate one material from another. And also the agglomeration became useful. When we did the computational modeling with means only, it actually was our new measurement of agglomeration, which was fitting with the toxicity outcomes, as opposed to the means of length or the means of diameter. So agglomeration is also very useful. One thing we found too is this helps streamline the needed characteristics in toxicity testing. Before, we were doing just this enormous battery of physicochemical characteristics, toxicity testing. This really can streamline this into a meaningful manner as well. Then some of our constructive feedbacks and comments are, we want to illustrate, we want to emphasize proper interpretation of what these outcomes mean. In other words, what does a yes outcome mean in terms of mesothelioma? For example, if you put Mitsui 7 or the traditional benchmark material into the pleural space, you can get mesothelioma. But the long-term inhalation study that induced pulmonary cancer highlighted the point that perhaps did not have mesothelioma, and not enough of the burden was reaching the pleural space in those studies. So I think, what does a yes outcome mean? needs to have some context with it. And then extrapolation to deposited dose is really something we get back from the industry when we work with recommended exposure limits. How much material does it take for this to happen? And obviously on the consumer side, that's going to be dramatically less compared to protecting the workforce. The IATA uses sort of secondary surrogate markers in terms of frustrated phagocytosis with inflammasome induction. You don't really need frustrated phagocytosis to induce the inflammasome, and induction of the inflammasome is not always linked to mesothelioma. So I think we want to also illustrate that we need a stepwise progression, that if the physical dimensions are putting us through to in vitro and in vivo testing, then these become secondary confirmation of some of those results that we found. In our studies, the outcomes both in vitro and in vivo seem very consistent with the dimensional analysis that we're finding. So there could be some usefulness here, but also, again, that proper interpretation of what we're looking at. Other recommendations for people who are doing these studies are temporal. When do people look? For our data, we use 7 days post-exposure. That sort of eliminates the effects acutely, and then we can see where's this sort of more sustained innate response. It gave us a much better separation of which materials had more potency versus others. And obviously dosing, what should people be using? Fiona touched on this, transitioning out of the mesothelioma harm to fibrosis or cancer. Multi-walled-1 is very unlikely to, is very unlikely to induce mesothelioma, but that does not mean that it won't induce pulmonary cancer. And sort of the last one, where do sort of plate-like structures fit? So these can be high aspect ratio nanomaterials, but they're not really the traditional fiber shape. So I don't know if they necessarily have a great home in this HARN IATA, and more relegated to a different one. But those were some of our comments that we found working through this. But overall, I think our data was a very good complement to Fiona's internal case study. And I think we extended some of those data gaps and shown how useful they will be. And with that, that's all I have.
Thank you, Aaron, for this excellent presentation. I think now we can open up a little panel. Maybe you can stop sharing your screen, and Fiona and yourself, if you like, you can switch on your camera. And there are a couple of questions already coming in from the chat, and I think we will start with those. And I would firstly give the word to Vicky, as she raised several questions.
Thank you, Andrea. I wasn't expecting to speak, so that was a shock. So I think my first question that I came across actually was in relation, there's a similarity between both talks in terms of how you started to characterize the different structures that the carbon nanotubes agglomerated into. Were you able to generate any sort of guidance or rules on how to characterize those? Because when you looked at your cartoons, your diagrams in Fiona's slide, they looked very clear, but when you looked at the SEMs, they weren't always that clear. So did you come up with any kind of rules or guidance to help with that?
Well, Vicky, what we've done is we're currently looking at GEM and SEM of this panel of case study materials. So we're a little bit behind on that. So we had sort of proposed these 4 different categorizations based on kind of our kind of conceptual idea of the sort of broad categories they could fall into. And we're trying to back that up now with actually looking at these case study materials that we've assessed by EM based on the same or a similar approach taken by NIOSH, where we're looking at dispersions or suspensions of these materials dispersed with some protein present, to see if we get a similar replication of what they have seen previously in terms of them being quite similar to what's been identified in workplace exposures.
Yeah, Erin,
So we
those
have that
pictures-
that's ongoing at the moment, but we haven't. We'll hopefully be able to illustrate these 4 broad groupings with these images, or else we'll try and change the groupings that we've proposed, or the categorizations we've proposed based on our real life case study images.
Yeah, I thought that was a really useful thing actually that Erin showed from their publication, is of how the suspensions looked in the lab versus how they looked when they extracted them from the lung and the lung lining fluid with the cells. That was really, really powerful. And the observation that you've only got 5% of the fibers as single carbon nanotubes. In the past, I think people have gone to great extents to try and disperse their particles as much as possible, but actually that isn't what people are exposed to. So I thought that was really, really useful. Andrea, I know that Rachel and others have got questions, so I can always ask questions another time. So if you want to prioritize them in the chat, I can always pop in later if we've got time.
No problem. And also what I suggest, maybe Fiona and Aaron can answer all the remaining questions then in the chat after this discussion. So there was a follow-up question on this 10% threshold, which I actually asked initially, and then Rachel followed up on that. So you said it's pragmatic, but maybe you have some more insights, and specifically Rachel, maybe Rachel, you want to show yourself directly, was following up. Is it related to mass or fiber number or other dose metrics? The threshold in length are on the 10.
Yeah. For that's we've had that exact question. Can we determine from we haven't done it yet, but can we determine from our toxicity outcomes what is the % threshold that you need to cross to have this switch in sustained inflammation, sustained pathology, and things like that? We haven't specifically done the math on it. We know it's a small number. We don't need a tremendous number of longer length tubes to induce the pathology, but it is a really good question, and I think in the future, our data, we can start mining that out and see if we can come up with what that % threshold is.
Thanks very much. I just follow up. I think it's very interesting what you're doing in terms of all the detailed characterization. We recently did a 28-day study using NM401, and we've been looking at using a nano-Moody to separate out the different sort of aerodynamic size bins and looking at the shapes and within that as well, because it's very difficult to link up. Well, that would allow you to sort of link up the deposition with the sort of particle shapes and sizes within that, because they're quite complicated aerosols, aren't they? And I just wondered if that was something that you looked at, because one of the things we're concerned about is a lot of the modeling of deposition is based on models that haven't really been very well validated against actual data. And one of the issues is things like the density of some of these particles and how you determine it. And I think some of the data you've got in terms of characterization is really nice. But I just wondered, am I getting too complex in terms, or do you think, you know, just looking at the length distribution overall, rather than say the length distribution within aerodynamic size bins might be, you know, taking a step too far unnecessarily, or might that be a valid approach?
We feel that we have, I've looked at all the tox data. Unfortunately, it's still some of it's still under review, getting into clearance, but looking at that data as a whole, we were really able to segregate out the materials using a isopropyl sonication just to create individual nominal tubes. We didn't have to look at aerodynamic size bins and things like that. We basically we created a scenario to get the individual tubes through an isopropyl alcohol, and we did 200 individual tubes, length and diameter from them, and that was enough to have essentially the predictions and the linking to all the toxicology. So in other words, from the lead end, our sort of general conclusion would be knowing what we put into the aerosol or what we put into all of our experiments, if we know what the individual tube is that's making up that sample, it will then follow through and create the toxicity. So I think the way that we learned that too is with the complementary bundled agglomerate analysis, where when we saw the increasing length and diameter, it immediately shifted how the bundled agglomerates formed. So in essence, to answer your question, I think the individual nominal tube assessment creates the aerosol form. It creates how the material agglomerates into bundles. So they're interrelated. So when we modeled the length bins with the bundled agglomerates, they kind of bin together, showing that these individual nominal tube measurements were really what was driving how the bundled agglomerates form. So from my perspective, we haven't seen the need to do anything beyond just a really good isopropyl sonication, getting this size distribution profile of these nominal tubes. So that's where we were hypothesizing we could go. That would very much limit the characterization needed if we can get to the final toxicity outcome from just those sort of 200 counts.
Yeah, no, that's fascinating. Thanks very much. I know there's loads of questions there. I want to ask more, but I will leave it there. Thank you very much.
Okay, thanks, Rachel, for asking. And there are 3 more questions that we can manage before the break. So the first one is from, let me check, Elisa, I think, concerning the rigidity and stiffness. And then there is one from Begona on the impurities and functional group, and another one from Wendell. So let's start with, I think it was Elisa. I hope I pronounced correctly. Elisa asked, how do you correlate rigidity and stiffness of the multivol CNTs to your outputs? Can we use rigidity as a common parameter? Maybe both of you could answer that.
I think when you talk about rigidity, we need to differentiate between if it's a rigid on an individual fiber level or the rigidity of the agglomerates that we see. So I think that is something that we were really trying to address with trying to better categorize and define our agglomerate structures, because if you have a bundle of very thin fibers, they might present as more of a straight, rigid, individual, long fibrous bundle. So I think that is something that we would consider important when we're considering the rigidity, that it might actually be more the agglomeration status. How you define and categorize that would be the parameter that you would use for grouping rather than rigidity of the fiber itself.
Okay, and Elisa more specifically asked also, is rigidity a common parameter for grouping of different chemical composition harms? Maybe Aaron, you can say a word on that.
I know going through some of the framework stuff in our interactions as well, we didn't measure rigidity specifically in these materials. We had thought about doing it, but maybe it is okay just to use the diameter as an inference of rigidity in this case. I don't think a specific measure of rigidity would actually change the outcome that we saw versus using our profiles of diameters combined with length. That's kind of how I would answer that question. I guess the broader part is, do we need rigidity to make the decision or the outcome? From our data, I don't know that we would need it. And I think we do have, I think it was a 30 nanometer cutoff was sort of the inference into rigidity. And most of the materials that we had that were a yes all had greater than 30 nanometer consensus diameters in those materials. And all the ones that were no with shorter length did not exceed that 30 nanometer threshold.
Maybe we follow up with Begona's question. Sorry if I'm a bit short. Begona is, I hope I pronounced correctly, Begona is asking where the impurities of functional group on the surface somehow considered in the toxicity assay, and would there be difference in the results among the different CNTs or carbon fibers? Level of impurities or surface coating. Is this somehow relevant in your case study?
We didn't do anything with, we did some studies with surface coatings, but not in this analysis. So functional groups on the surface, we didn't reference as a change here. But as far as impurities, the metal catalysts did not play a role in defining these materials for our toxicity outcomes.
I think from our point of view, so looking at the surface defects or impurities might be useful when you're conducting your similarity assessment, but I don't think it's fundamental for the preliminary grouping as a biopersistent rigid high aspect ratio nanomaterial as we set out in this IATA. But if you want to consider the potential similarities and potency of response to different nanoforms, if you want to look at for supporting your read across argument, it might be that one with a high level of impurities, you would expect to have a greater inflammatory response to genotoxicity rather than one with lower levels. But I think this is something that you would look at in your further studies on the toxicity endpoints.
Okay, and then it's not a question, it's more a suggestion by Wendel. If you would think it could be a good idea to rename the Hahn YATA into a fiber YATA. There are other people commenting on this suggestion. Wendel, would you like to speak yourself about that idea?
Thank you, but I think it's obvious. It's just the lack of examples. We cannot justify the inclusion of platelets, and Aaron also seemed to comment in this direction. So what do you think about it?
Yeah, I can't disagree with the suggestion of changing it to a fiber IATA, because we're going to have other high aspect ratio materials that don't really fit what you would consider to be a fiber.
Okay, Vicky is raising her hands before we go to the break.
Yeah, I actually was thinking as Aaron and Fiona were presenting that we're missing a case study with platelet-like materials. And this might be something that the new projects Sunshine, Diagonal and Harmless might consider including in there. So I think it would be really nice actually to try and create an IATA that would be suitable for these types of materials.
Yeah, I would agree to that, certainly. And hopefully there will be a chance in these new projects to work on these cases. For the time being, I think we are perfectly in time. And at least in the chat, there are no more questions. And also I see no more raised hands currently. So I can only say thank you very much, Aaron and Fiona. And in case you have other questions that come into your mind later on, you can still put them in the chat. And I'm sure Aaron and Fiona will follow the chat and answer the questions dedicated to them. So that brings us now to a 10 minutes break. And before doing so, I will share again our little survey from the beginning. Maybe while you grab a coffee, you still would like to answer these two questions. And with having said that, see you back in 10 minutes time. Have a good break. Okay, so welcome everybody back from our break. Before we continue, I will share a last time the survey, which I'm going to stop now, just to let you know. The first question on menti.com was about the country, where are you, from which you are joining the event. And you see, obviously, Germany is well populated, but we have a lot of other countries as well, which is very good to see. And the second question was the type of institution the participants are working for. The majority comes from small company and private business, and academic institution is a second most popular group, but also regulatory agency, large companies or other institutions are presented. So while the next session is ongoing, I will definitively stop the survey because we will need it later on. And now it's my pleasure to hand over to my colleague Eric Plicker from RFIM, as he will take over the chair position for our next session on environmental aspects. Eric, please, the floor is yours.
Thank you, Andrea, and also a warm welcome from me to all everyone present. And I don't have prepared any. I didn't prepare any slides. Just I'd like to simply start with the first presentation on the environmental side, which will be given by Willy Pijnenburg from RIVM on a first internal case study. Willy, go ahead.
Thank you very much, Eric. Oh. If things are okay, you can now see my screen.
Yeah, that's correct.
Okay, and then I need to do this. All right, what I would like to do is to talk about similarity assessment of soluble metallic nanoparticles. What I want to show is an approach on how to deduce aspects of similarity across a number of nanoparticles of the same composition, but of some different properties. In this case, the focus will be on size to allow for a predictive approach towards their toxicity. Now, the case study is related to the one of the aquatic hypotheses related to the link between dissolution rates and toxicity. And in the IATA, there are a number of options given with regard to the ratio of dissolution rate and toxicity. Now, I've modified it a little bit and focused only on the dissolution rate in what is shown on this first slide. And I've made a distinction between quickly dissolving nanomaterials, very slowly dissolving nanomaterials, and slowly dissolving nanomaterials, with the definitions of quick, very slow, and slow still to be decided in terms of dissolution rate constants. But in the first case, and that is here the indication EG1A, when there is a nanoparticle that's very quickly dissolving, then it will be the solutes that drive toxicity of the suspension. In the second case, EG1B, when the dissolution is very slow, or if the particle doesn't dissolve at all, of course, it will be the nanoforms that determine toxicity. And in the third case, when the dissolution rate is in between quick and very slow, then it's the combination of both the toxicity of the ions or the solutes in general and the nanoforms that will drive the toxicity of the overall suspension. And the focus of my presentation will especially be on the last case, where there is a contribution of both ions and nanoforms on toxicity of suspensions. Now, when dealing with toxicity of suspensions or the ecotoxicity of soluble metallic nanoparticles in general, 5 different things are into play. And I will illustrate each of these 5 different issues later on in my presentation. Well, first of all, fate assessment, it's essential. So what is needed when you have dissolving nanoparticles is to assess the fate of both the nanoparticles themselves, the nanoforms themselves, and of the ions that are being formed in the case of the metallic nanoparticles. Dissolution modeling as second step is part of that fate assessment, and this is especially assessing the kinetics of dissolution so as to be able to determine the concentration of particles and ions over time. Third step is the effect assessment. That is actually performing the ecotoxicity testing of the suspensions of the nanoparticles over time. And the outcome of effect assessment for various nanoparticles are then used for effect modeling to derive a predictive model for the toxicity of the sets of nanoparticles that have been tested. And then finally, there is the issue of similarity modeling. Now, to start with the fate assessment, what is done here is relatively simple. It is determining the concentration of the particles in solution as a function of time. And here are some examples of concentration time curves that can be generated for different types of nanoparticles. And here in all cases, some shapes and some sizes of nanoparticles have been measured, and their fate has been assessed as a function of time. And what results out of these assessment is the time-weighted average concentration of the particles in suspension. And this time-weighted average concentration can be used as the basis for the dose assessment later on. Now, the same can be done for the ion concentrations, of course, and what you typically get is an increase of the ion concentration as a function of time, as shown here. And here too, the outcome is the time-weighted average concentration of the ions during the toxicity testing. So this is step one. Step two is dissolution modeling, and that is, as I said, part of the fate assessment, as the fate of the particle is to a certain extent determined by dissolution, but also in the case of some specific nanomaterials, for instance, by sedimentation following aggregation of the particles. Now, with regard to dissolution modeling, the dissolution rate overall, it is dependent on some of the intrinsic properties of the particles. First of all, of course, chemical composition, but also size, shape, and the presence or absence of coatings are determining the rates of dissolution. And then the composition of the medium is also of importance. So that's an extrinsic property that's also determining the rate of dissolution. And here things like pH, DOC, nanoparticle concentration, they all come into play. And what is shown here is an example out of literature where the dissolution of silver nanoparticles was measured as a function of time. And what you can see here is the impact of size, with the smallest nanoparticles overall having the highest extent of dissolution after a given period of time. And in this case, the experiment was run for more than 300 hours. And the data that are generated, they can be used to mathematically model the rates of dissolution. And here is an example of a model that we derived, a mathematical model, to determine the ion formation as shown on the left-hand graph, but also to show the difference in size distribution, the shift of that size distribution as a function of time, given a specific size distribution of a mixture of nanoparticles in suspension. And in this case, the modeling was performed for, after 300 hours. Oh, sorry. After 300 hours of exposure. And what you can see is that despite the kinetics of dissolution being relatively high, still the size distribution shifts only a little bit after this exposure time. Third step is the actual effect assessment, and this is an example with zebrafish embryos, where the embryos were exposed for a fixed period of time. In this case, it is 4 days overall, and what we did was do all the steps that I have explained before, and what you then get is dose response curves that look like this, with mortality on the y-axis and the actual concentrations of the initial concentrations of the particle on the x-axis. And what you can see in this example is that in general, the smaller the particles, the more toxic they are, and that is reflected by the most toxic particles being displayed here on the left-hand side of the dose response curves that are shown here. Now, in numerical sense, having these dose response curves and having deduced the effect levels that originate from these dose response curves, it is possible to calculate the contribution of the particles and of the ions to toxicity. And to do so, we first of all need, of course, the measured concentrations of the ions and of the particles as shown before, and then we can assume that we get a mixture of particles and ions in which both the ions and the particles contribute to the overall toxicity. And we can then use the basic rules of mixture toxicity as being developed, for instance, for organic chemicals, to model the contribution of each of the constituents, the ions or the nanoforms. And in this case, we use the response addition model, assuming that there is a difference in toxicity, in mechanism of toxicity of the ions and the particles. In this equation, we have measured the effects of the mixture of the overall suspension. So that's the mixture of the ions and of the nanoforms. Separately, we have measured the toxicity of the copper ions, and that means that the only unknown is the toxicity of the copper nanoparticles in suspension. Now, and when we apply this model to the data generated, taking into account the measured concentrations and the measured effect levels, we get the following overall result. What is shown here is the LC50 value, so the value, the concentration at which 50% of the organisms dies for both the overall copper nanoparticle suspensions and for the actual particle form of the copper nanoparticles. So this is really the nanoform with a specific size, specific spherical size that is causing toxicity. And what you can see is that indeed the LC50 values of the smallest nanoparticles, they are the lowest. So these particles are the most toxic, and there seems to be a trend that upon increasing size, toxicity is decreasing. So the LC50 values increase, and the exception seems to be the 400 nanometer particle. What is also interesting to note is that the copper ion is relatively toxic. It's in between the toxicity of the 25 nanometer particle and the 50 nanometer particle. And this is the value that has been used for the correction of the LC50 values generated for the copper nanoparticles. Now, the fourth step is to derive a model. And what is shown here is a plot of the LC50 values of the nanoforms as a function of the diameter of the particles. Now, on the x-axis is the log transformed diameter of the nanoparticles, and on the y-axis is the log transformed number of particles in suspension that is needed to cause 50% mortality of the zebrafish embryos. And what you can see is that there is a relatively good fit between the number of particles needed to kill 50% of the zebrafish and the size of the particles. And what's also important is that the slope of this curve is around -3. So this is one way of modeling the effects of a series of spherical copper particles. Now, the same can be done for silver nanoparticles, of course, and that is what we also did. And the results are shown here on the right-hand side. And then two things are of importance. One is that the slope is again almost -3. Again, the goodness of fit is it's fine. And in this case, the fixed value of the equation, it is different. And this implies that silver nanoparticles, silver nanoforms are by 2 orders of magnitude more toxic than copper nanoparticles of the same size. And this would basically be the toxicity prediction for a nanoparticle of 1 nanometer. So it is important to realize indeed that it can be concluded from these two curves that copper nanoparticles are by 2 orders of magnitude less toxic than silver nanoparticles. And that is in terms of the number of particles needed to kill 50% of the organisms. Now, these equations, since the slope is the same, they can now be used for predicting the toxicity of a unknown nanoparticle of a specific size, provided that for a nanoparticle of another size, a toxicity result is available. And that is schematically shown here. Suppose we have a nanoparticle which size after log transformation is around 2.5 nanometers, so it's more than 100 nanometers of size. And we have another part, then we can make a prediction then we have a measured value, excuse me, of toxicity, and then we can use the slope of -3 to make a prediction for any other sized nanoparticle. So this would be the approach for similarity assessment for calculating the LC50 of non-tested metallic nanoparticles. Now, and here are some examples where it is shown that it does work with some particular results, because what is shown here is again the equation for the copper and the silver nanoparticles that I've just shown, but now an example has been added of a data set of silver particles that were coated with phosphate. And in the case of phosphate coating, there is no release of silver ions. And apparently that causes the particles to be less toxic. And in this case, the value is not given, but it means that again, the phosphate coated silver nanoparticles, they are by 2 orders of magnitude less toxic than non-phosphate coated silver nanoparticles of the same size. And again, what you can see is that the slope is virtually -3 as well. And now the same approach can be followed not only for zebrafish embryos, but we have also data that are similar for daphnids, algae, for instance. But it's also possible to use the same approach to make predictions for different endpoints. So it doesn't only work for LC50 values as shown in this example, but it does also work for EC20 values, EC40, EC60, etc. And in all cases, the basis of the similarity modeling is the relationship between the log of the diameter and the number of particles after log transformation, causing a certain effect level, EC20 up till LC50 or EC50. Well, the approach doesn't always work in the sense that here is an example of the dissolution kinetics of zinc oxide nanoparticles and copper nanoparticles that were used for exposure of lattice in a specific medium of a relatively low pH. In this case, the pH was a little bit above 5. And what is happening here is that the copper and the zinc oxide nanoparticles, as shown on the left-hand side of this graph, they dissolve very quickly. And what you can see is that, well, within 1 or 2 hours, more than 80% in some cases of the particles has already dissolved. So their contribution to toxicity, it will almost be negligible. It's just a few percent, even after, especially after long-term exposure, of course, of the lattice to the particles in this medium. The other example where the approach doesn't work in the sense that the basic principles of limitedly quickly or limitedly slowly dissolving particles is not met is the case of barium sulfide. And what's happening there is that the particles are stable, but they will sediment very quickly in this medium. And what you can see is that, well, within half an hour, only less than 1% of the particles is still in suspension. So what's happening here is that you see no toxicity because there is no real exposure of the particles to the barium sulfate of the lattice plants to the barium sulfate nanoparticles. And with that, I would like to thank you for your attention. Thank you.
Thank you, Willy. And I'd like to remind the participants that they can put their questions in the chat if they want to, and then we'll come back to that in the discussion. But first, I'd like to give Koen the floor for the external case study by the Zinc Association. Go ahead, Koen.
Okay, thank you, Eric. Let's share my screen. Can you all see the presentation?
Yes, that's clear. Thanks, Koen.
Yeah, okay. So our presentation is about the grouping of zinc oxide nanoforms for aquatic toxicity, and it's in fact a collaborative project between the International Zinc Association and Arch Consulting A bit of background on this project. Why did we step in? First of all, zinc oxide has been registered on the REACH, and the REACH dossier covers several nanoforms. And these are covered mainly via the ion hypothesis, being that all effects, being human health or environmental hazards effects of the nanoforms, are expected to be covered by toxicity data for the zinc ion. Now, there have been some concerns on specifically the environmental effects assessment from an evaluating member state that challenged this hypothesis. And they want to see more data to really justify the hypothesis, and to also really see that justified for individual zinc oxide nanoforms, while now we only had a general statement. So because of that, a lot of data have been generated, and it looked very interesting to us to also test all this data for the GRACIOS framework for the grouping of zinc oxides nanoforms for aquatic toxicity. So with all these data, and if we follow the IATAs and the decision notes from GRACIOS, where would we end up? So the purpose was regulatory compliance, REACH related mainly. In total, we had these 28 zinc oxide nanoforms, varying in size, shape, and also coating. And the main focus was this aquatic grouping hypothesis. So to see if the aquatic toxicity for all nanoforms could be covered by data for soluble zinc salts as a realistic worst case. So we did not follow a specific IATA. In fact, we took the most important decision notes for these IATAs for aquatic environments. And these are the ones for dissolution, dispersion stability, and the toxicity ratio of the solute versus the nanoform. And then in the end, we will see where we will end up, in which hypothesis we would fit. So the first decision note is on dissolution, and there are several tiers of data that you can provide there. The first tier is batch dissolution tests, 24 hours. And in higher tier, it goes to continuous flows in standard media or in specific test media. And in the guidance, some provisional cutoff levels have been reported for read across. And quick dissolution is defined as more than 90% dissolution for each of the pH levels. Very slow is less than 10%, and all the rest is intermediate. So where do we end up with the data? In the left columns, you see the 28 nanoforms. The upper two, so 368 and 369, are in fact two standard nanoforms that also have been tested a lot by GRC and also partly in the GRACIOS project, I think. You see there are different shapes, tubular, spherical, plates, and so on. The particle size ranges and also the coating is also quite different. But despite all these quite strong differences in nanoforms, what do we see in tier 1 batch dissolution test? And that's a 24-hour transformation dissolution protocol-like test at 100 milligrams liter, 100 milligrams zinc oxide per liter, loading in standard Ecotox medium with pH 7.6. And we see, in fact, that overall these 28 forms, the percentage of zinc oxide that's been dissolved after 24 hours is between 2, 3, and 10%. So always below 10%. We did not have any tier 2 data. There's one data point on the first nanoform that we took from the GRACIOS project, but we also have some results from tier 3. So dissolution in relevant media, in algae and Daphnia media. It's not a continuous flow, but it's a batch dissolution test. And I will show the results more in detail in the next slides. So first of all, the dissolution, the tier 1, the data from the transformation dissolution protocol. So 24 hours loading rate of 100 milligram zinc oxide per liter. And 2 different fractions have been measured. One so-called dispersed fraction. So that's a sample which has been filtered over 0.2 micrometers filter, and then the so-called truly dissolved fraction, which is filtered over 3 kilodaltons. And you see results after 6 and 24 hours. And for each nanoforms, you have 2 columns. One is the dispersed, the first one, and the second is the truly dissolved. And you can see that both columns are the same for the vast majority of the cases. For the 6 hours, only for 2 nanoforms, there's a small difference between the two, meaning that there is some nanosize fraction present. So a fraction between smaller than 2 micrometers and not being truly dissolved. But after 24 hours, we don't see any nanosite particles anymore in these samples. So it's either dissolved or larger agglomerated to particles larger than 0.2 micrometers. Then the dissolution data for tier 3, so the data from tox tests from algae and Daphnia media. So these have been tested for 3 particles, the 368, 369, and the 410. So this is the standard one, non-hydrophobic. 369 is a hydrophobic coated, and 410 are plates. And what can we see here? With 3 fractions have been measured: the total zinc in solution, so an unfiltered solution, then the dispersed, smaller than 0.2 micrometers, and the truly dissolved, so-called truly dissolved zinc, so filtered over 3 kilodalton. The first thing that we see again here is that the dispersed and the truly dissolved are virtually the same or almost the same. So there's no indication for the presence of particles smaller than 0.2 micrometer. I also have to say these results are time-weighted average results from over the course of these toxicity studies. The algae medium is 3 days. The Daphnia toxicity study was at 28 days, but semi-static, so solutions have been replaced every 2 to 3 days and measured at start and end of every replacement. What do we see else here is that for the percentage which is dissolved or dispersed, it's almost the same, decreases with increasing total concentration in solution. So you go from more than 70% or 60-70% at low concentrations to less than 10% at higher concentrations in above 10-20 milligrams zinc per liter. For the Daphnia medium, there was less variation in exposure concentration, so that's also translated in less variation over the doses in the amount that's been dissolved. So what did we conclude from all of this is that according to the tier 1 tests at 100 milligrams per liter, in fact, we should screen this out, zinc oxide out as very slow, slowly dissolving, less than 10%, but it's partly dissolving 10 to 90% according to the tier 3 results at lower test concentrations and in relevant media. And so far, we did not see an indication for the presence of nanosized particles in the ecotox media because this dispersing fraction, so smaller than 0.2 micrometer, is always similar as a truly dissolved zinc fraction. When we go down to the data that we had for dispersion stability, there a tiered approach is again proposed by the GRACIOS framework within the first year, the screening dispersion test according to the OECD guideline 318. In tier 2, you have then the extended dispersion test with and without organic matter with different time points. And tier 3 is done in specific test media. And you also have some standard cutoff values here. A stable dispersion is defined as more than 90% in dispersion under all test conditions, so all pH levels, all ionic strengths, all with and without organic matter. Unstable is less than 10%. What do we see for these 28 nanoforms that have been tested? They all went through the screening test, and almost half of them went through the extended dispersion stability test. And what do we see? That at pH 4, for example, all or virtually all samples are fully dissolved, so which is in fact a false positive. Apparently it's stable because you measure all the zinc in the water column, but it's completely dissolved at pH 4. Another issue that we experience is with the hydrophobic samples. As you can see on the picture above, the two left beakers, where you clearly see that they are on the surface of the water column and not within the water column. So only 5 to 10% is transferred in the actual water medium after sonication, and all the rest is still floating above. So for these hydrophobically coated substance, we did not do an extended test, as we found that not really useful. For all the other ones, in fact, the intermediate or both the screening test and the intermediate test gave the same results, that their intermediate stability. But here, yeah, we were lacking a bit of guidance on how to interpret this solution, and mainly on how to go along with the hydrophobic samples. We'll show the data a bit more in detail. These are the results from the screening test. As I said, all intermediate. There was only one out of the 28 nanoforms that showed a high dispersion stability, so that's more than 90% dispersion throughout all the treatments, being the 3 pH levels and the 3 concentrations of calcium salt in it. That high dispersion stability sample, that's that number 410, the uncoated form with that are platelets. If we go then to the extended test, there we see that for all the cases, it's an intermediate. We see different responses from few percentage stability, dispersion stability, to over 90%. So overall, it's all intermediate. So far, it's quite consistent across all the 28 nanoforms. They all partially dissolve, and they all show a similar dispersion, intermediate dispersion stability. Then finally, we looked at the toxicity ratio of the solutes versus the nanoforms. That was not done for all the forms, but 3 were selected. I presented these already. That's then uncoated tubular with an intermediate dispersion stability, then an hydrophobic coated, also tubular form with low dispersion stability, and finally that platelets that had the highest dispersion stability. 2 tests have been performed, a chronic Daphnia magna test and an algae, a standard algae test. Next to these 3 nanoforms, also zinc chloride has been tested. And then again, the same analytical measurements have been done. So total zinc concentration in solution, so in the water column, total dispersed, or the so-called dispersed fraction, smaller than 0.2 micrometers, and the truly dissolved zinc fraction. Here I have to say that after checking and checking again the results from the measurements, analytical measurements, we found some analytical issues. There are indications for some of the nanoforms for blockage of the filters. So the presence of larger particles in the water column, in the sample, can block the filters, and we found a potential underestimate of the dispersed and truly dissolved concentration of up to a factor 2 if you work with small volumes, always with new filters instead of filtering a larger value through one filter. That can make quite a big difference. And also the hydrophobic samples are clearly not homogeneously distributed over the water column. So the sampling location, if it's more on the top, in the center, or at the bottom, really affects the results. And here I have to, again, to give the same message that so far we did not see any difference in concentration of the dispersed and truly dissolved fractions, so there's no indication for the presence of really nano-sized particles. Then going to toxicity data, first we just compared the EC10 and EC50 values between the nanoforms and calcium chloride based on these 3 fraction measures. And if we compare these values, the EC10 and EC50 based on the total ECX, so based on the total fraction zinc fraction in solution, then we always found ECX values for the nanoforms, which are above or similar to the ones for the zinc ions, so the zinc chloride. So which made us decide that nanoforms are not more toxic than zinc ion based on the total zinc concentration in solution. If we go then to filtered fractions, so either the dispersed or truly dissolved, and the results for the two are almost the same, there we see that there are some differences, but that EC10 or EC50 values for the nanoforms are generally within a factor of 2 of the EC10 or corresponding EC10 or EC50 for the zinc ions. Next to just these comparisons, we also predicted the contribution of the dissolved ions to the toxicity, in fact, based on what Willy presented in his presentation on this mixture toxicity approach, and based on the concentration of truly dissolved zinc measured and the toxicity, the measured toxicity of zinc chloride. And there we see that over all the tests done, that 30 to more than 100% of the toxicity of the nanoforms can be explained or can be attributed to the ions. Now this range, these values, they really vary not only among the tests, Daphnids versus algae, but also among the doses. Lower doses usually give more uncertainty, give a lower contribution or predicted contribution from the ions, while if we go to 20, 30 or higher % effect, then almost all the effect has been, could be explained by the ions. And we also saw some small variation among the 3 nanoforms tested. So yeah, here I want to say that we found that there's quite some uncertainty related with this comparison, because first of all, we have the uncertainty related to the analytics, what we measure or as the ions present in the nanoforms solutions. The ions, is that a true, is that the representative value, or is that an underestimate? There is also the uncertainty on the dose response curves. The further you go to the extremes of the dose response curves, the more uncertainty there is on the percentage effect predicted that you need for predicting the contribution. So there's quite some uncertainty, and this made us decide, so this uncertainty on analytics and on dose response fitting, and also the absence of identified nano-sized particles in the exposure medium during the test. Therefore, we concluded that there is no indication for a significant contribution, and significant is important because we will not say there's no contribution of the nanoforms to the aquatic toxicity, and that in fact the majority of the effects can still be explained by the presence of the ions. So bringing all this together, the information for these different decision nodes, this would lead us to hypothesis EG1D. So nanoforms that partially dissolve in a partial stable dispersion in environmentally relevant aquatic media. And there the data are quite consistent for all 28 nanoforms. And so it's clear that in aqueous exposure, there is exposure to the solutes and the particles. The only thing still under discussion, it's still a preliminary conclusion, is the toxicity ratio between solute and a nanoform. But for the moment, we think that it's a high toxicity ratio between solute and nanoform, and this still allows read across to similar solutes as a conservative estimate of toxicity for the nanoforms. Then in the last slide, I summarize some of the lessons learned. First of all, dissolution. It's clear that the percentage dissolution decreases with loading. So the concentration to be tested strongly affects the outcome and the category you will fall in, if it's quickly dissolving or not. So this needs to be thought over quite well before making your or designing your experiments. The results so far, all the results did not support quick dissolution for zinc oxide. In contrast, in fact, to what's usually reported also within the GRACIOS project, zinc oxide is often looked at an example of a quickly dissolving nanoform. So we did not see that. And next to the percentage dissolution, we also think it's important to consider the toxicity of the solute in decision on the relevance of the dissolution behavior. Because even when it's a particle dissolves less than 10%, but the dissolved fraction is way above the toxicity of the corresponding ion, this still may be a relevant contribution to the overall toxicity, and it should not be neglected. So toxicity of the corresponding solutes should be taken into account in the decision on the relevance of dissolution. Then dispersion stability. Yeah, as I showed, we have some doubts on how to interpret and how to on the reliability of the results for hydrophobic substances. And we also have some doubts on the question of the relevance of tier 2, which is the extended test in all the standard OECD 318 media, because for our cases and the 28 or at least 17 examples tested, then it all gave the same results, except for one that shifted from stable dispersion to intermediate dispersion. So the additional effort for this tier 2 is not really clear, and we would prefer to, if we do the full extended test, to really go into standard ecotox media, so tier 3 direct. And then on the toxicity, yeah, I think it's important to take into account, and certainly on the analytical measurements of the dispersed and the truly dissolved fractions, and on all the dose response curves and so on, into these decisions on comparable toxicity between solutes and nanoforms. For us, we found it quite difficult to really make clear conclusions there, but in the end, if we look at the total concentration and And that's what's usually measured in environment or in exposure assessments. There we think that the soluble zinc ion is still a conservative estimate for toxicity of all the nanoforms that were covered in this project. And this was my last slide.
Thank you, Koen. Maybe you can stop sharing and we can go to some of the questions. I realize that we are a bit behind schedule, but some of the questions, I hope you can have a look yourself at some of the questions which are more detailed, but I'm picking out one from Vicky who indicates that if you did your dissolution testing in static conditions, do you think the same conclusion would be made if you had used flow-through conditions?
Hard to say because we don't have this continuous flow. But I'm more thinking about the relevance of these results, because in your ecotox tests, as they are, these are also usually static or semi-static conditions. So this gives at least an estimate of what organisms are exposed to.
Oh. Okay. But you would then, for the relevance of your ecotox testing, you would suggest to look at the static conditions for your dissolution testing?
This is what has been measured in the, during the ecotox tests. So that's the actual exposure that has been measured there, and that we took also into account in the decision process on dissolution.
Okay, thank you. And please stay on. I might come back to you, but the next one is for Willy. Willy, what a question from Teresa. What is the best way forward regarding the interplay of the intrinsic properties? What are the lessons learned?
Well, I think there are 3 lessons learned. One is that chemical composition is very important, because it makes a difference whether you're dealing with silver or with...
Sorry, Willy, I'm now looking at Elise's, yeah, okay. I was looking at someone's screen, so... Okay, go ahead.
Well, the first lesson was that chemical composition is very important, because there was a clear difference between the toxicity of silver nanoparticles and of copper nanoparticles. The second thing was, and that is given the curves I've shown, that the size is important in modifying toxicity. And then finally, and that is related to the fact that all curves shown were valid only for spherical particles. But if we look at other shaped particles, then we find that the surface volume ratio might be a good predictor of toxicity. And that is for things like platelets, rods, all other kinds of shapes. If you put those on one pile, then that would be the overall descriptor that is determining best the toxicity.
Okay, so thanks.
Yep.
And a bit related maybe is regarding the solubility and the differences that Koen showed for the different media, algae and daphnids. How would that influence your interpretation, Willy?
What is very important for the particles that we studied, and also what Koen studied, is the pH of the medium. That is what we find to be the key property. And if I remember well, Koen's experiments were done mostly at the pH exceeding 6 or even close to 7. And I've shown an example for zinc where we did the experiments at pH around 5, 5.5. And what we found is that very quickly all particles had dissolved, which is different to what Koen found at higher pH. And I think this nicely illustrates the key importance of pH, and also size. Other things, they are important, but the key parameter that we found is pH indeed.
Yeah, I can only agree with that. As I said, in the dispersion stability test at pH 4, everything dissolved. And 2 ecotox tests, that was around pH 8 even. So that's at the other end of the spectrum for aquatic environments.
Okay, and then maybe a last question. Kun, you were showing that it depended a bit for your toxicity comparisons, whether you looked at the EC10 or the EC50, or and within Gracious, we have developed some similarity algorithms that consider the dose response curve as a whole. Would that improve your comparisons, or would that help in your comparisons?
Yes, I think that would be very useful to have some clear strategies or approaches on how to do that. In my comparison, to see how much the ions contribute to the overall toxicity, I took the concentration measured in the nanoform solution and predicted then the concentration of the ion based on the complete dose response curve for the ion. But we did not check similarity between those response curves, between complete dose response curves for the nanoforms and the solutes. So I think that would be helpful, yes.
Yeah, okay. I'm now looking at a next one from Richard Cross, comparing graphs from extended tests rather than final dispersion stability. Did you see differences between the nanoforms? And he gives examples of the shape of the curves in the extended test of time might differ. Or can you tell whether the particles are continually falling out of dispersion over time or whether an unstable fraction sediments quickly?
Yeah, I cannot say by heart. We have to go back to the data themselves. But the outcome was in fact always intermediate stability. But I have to check the curves again.
Okay. Because that clearly also influences a bit on how you look at your dispersibility. Let me see. I think that's more or less the questions, apart from some more detailed ones on specific tests. So I hope you can have a look at those in the chat and answer them there. And then looking at the time, I think it's good to move on to the next presentation.
Eric, I think we have time that you discuss like 5 more minutes, as we have plenty of time for the final overall discussion. So maybe just use a little bit more time to discuss the environmental case studies.
Okay. Let me then check if or someone can raise his hands if they want to while I'm looking at the chat, if they want to come up with their question, because see something else came up. Yeah, Vicky, go ahead.
Thanks, Eric. Cohen mentioned that for the coated zinc oxide nanoforms, he would have liked more guidance. I think, Cohen, you focused on the dissolution IATAs. Did you have a look at the IATAs for coated nanomaterials?
It was mainly on how to interpret the results for the dispersion stability, where everything was floating on top. There are indeed the IATAs for coated materials and how to check potential contribution of coatings to toxicity and so on. We left this for the moment out of our analysis. We focused on these 3 decision nodes, but yeah, we are aware that you have these IATAs as well, and the goal is indeed to also check these ones, also if coatings decompose rapidly, if they can contribute to toxicity and so on, to also do that.
Yeah, because if they lost their coating over time, they might become better dispersed, and then they might become better dissolved. And so, Eric, I guess that's something we just need to double check in the guidance that, you know, for that kind of case study, is there a clear link from the the outcome from that IATA that Cohen would have generated for the dissolution to link you into the coated, or perhaps there isn't a need for that because by filling in the basic information, the coating, the fact that there was a coating on the particle might have just triggered that coating IATA anyway. So maybe there isn't that link, but we should just double check that.
Yeah, I think there is that link that you would also be guided to the coating IATAs, but it's good to check.
Yeah, and Cohen, we will put you in touch with two of our colleagues, Nina and Georgia, who have developed the methodologies for dose response similarity assessment. Unfortunately, they're not so simple that you could just run them on your own computer. They're fairly, one of them takes like 24 hours to run. It's quite a complex algorithm. So you have to kind of hand the data over to Georgia for her to do that. So it's whether you're happy to do that or not. Whereas Nina's, I think you might be able to do more in an online format.
Yeah, we can do this online. So it's a seconds. Not. I'm really surprised from 24 hours.
Yeah. So there are two options there. We can look at them afterwards.
And Richard, maybe you want to elaborate a bit on your remark on similarity assessment of curves, scalar descriptors, or is this related to that?
Oh, that's just been answered by Vicky, yeah.
Okay. And that was done with, I think we more or less covered all comments in the chat. So thank you for your...
I've got a question. Can I ask a question?
Yeah, sure.
Given that this time anyway, I think what Andrea said. So I was asking about, I've been thinking about it in terms of formulating it, but asking about the dissolution in the different media. And often people say there's not a big difference between the algae and the Daphnia media, say, in terms of dissolution, but of course there's not always the case. But I think Cohen has actually demonstrated differences. Although you use the different range of concentrations, I try to compare the kind of similar concentrations for the two media, and there were differences indeed. So when you actually look at, I was thinking about what you said really in terms of extrapolating different species, because you did zebrafish and you did the plant, and then Cohen did the more traditional algae and Daphnia. So how do you resolve that? Do you need to go and actually do all the dissolution work first, and then to actually use the models to extrapolate, etc.? I mean, what would be the best way around? I realize it's quite a lot of there's quite a lot of different parameters to consider, and this is not new, but it's nice to see some of the data to illustrate some of these points and to help us think about them and how you use the data to test the IATAs, etc., and then refine procedures. So yeah, I mean, this could be just a topic for a bit later, or if you want to address it now, both Willie and Cohen, that could be great. Thanks.
Yeah, I think Teresa, for different media, you always need some idea on the actual concentration. So you always need to do some measurements of some analytical measurements of the fate in the media, and it might be possible if we would more systematically compare data that have been generated in several media to derive a model perhaps that can be used to compare, for instance, rates of dissolution, or to make comparison on the extent of dispersibility. Although those models do not exist at the moment. I think that answers your first part of the question, I guess. And when that's done, as I've shown, it is possible to derive predictive models for toxicity once those data are available. And that is relatively straightforward. Just as in the past, we developed QSARs for organic chemicals. Yeah, basically we do the same.
Yeah, so I guess it's more complicated than just saying if we extrapolate from one species to another. We need to bear in mind that the fate of the particles is likely different, let alone what the organisms do and everything else. But just concentrate on that, what they might do. So yeah, okay, thank you.
Okay, thanks. And thank you, Koen, and thank you, Willy, for your presentations and your answers in the discussion. And I hand it back to you, Andrea.
Thank you, Eric. Also, thank you for taking over the chair for this second environmental session. Now we are coming back to human health and to inhalation, but from a completely different angle. And this is for the first time now we look into grouping of across different substances where we included a pigment case study. And I think, Wendel, you will be the presenter for this case study?
I will. Let me share the screen again. So I hope you can see the full screen mode now.
Yes, it's fine.
Perfect. So it's my pleasure to present a case study that we start with Gemma and Nina. Unfortunately, Gemma is no longer working on the project, but she shaped the start of it. And lots of the data also comes from LANMAR because we are using both tier 1 and tier 3 data. The scope here is to look at 11 substances with complete tier 1 and tier 3 data. And like Andrea introduced it, it is about inhalation. Especially it's about the hypothesis that we will have a similar hazard by the inhalation of very slowly dissolving and very low reactive nanoforms. And so the purpose of grouping here is not regulatory, simply because the ECHA guidance doesn't want to see cross-substance nanoform grouping, whereas that is not excluded by REACH. So at least it's interesting to consider. The way we proceed here is that we perform all of the testing that's required in tier 1. And for the specific materials, we also have the qualitative and quantitative assessment of tier 3, which means the in vivo inhalation studies. We also include some non-nanoforms of the same chemical substances to also enable that comparison between nano and non-nanoforms. As I'm going to show in a second, we are using 5 diketopyrrolopyrrole pigments, that's DPP, 2 diarylite pigments, it's actually more, it's 4, I think, a monoazo pigment, 2 copper-phthalocyanine pigments, and 2 paralenes. It's important to mention that some of them have been available to all of the GRACIOS consortium, but not all of them. And that's why it is really a case study that goes beyond what was available in GRACIOS. This specific pigment blue 15.1, which is a copper-phthalocyanine, was also available. And the nano and non-nano form of the DPP red 254, which is a diketopyrrolopyrrole, have also been available. We have now added, as you can see, different versions of DPPs, etc. For all of you in the GRACIOS consortium, you know what pigments are because you have been working with them over the last years. But for the others, I wanted to highlight that organic pigments are particles that consist of small molecules. So we also highlight here the molecular weight, which is below 1000. And here you see typical formulas. So these particles are held together by very strong van der Waals forces. So because these are quite hydrophobic substances, they are held together by van der Waals forces, or in some cases by complexation with counter ions. And this is then called a metal lake pigment. There's also a third case where the metal is only complexed, but it's not actually holding the different molecules together. But it's part of the synthesis process also. And so a pigment, by definition, is not soluble in the intended use, which means in an automotive coating or in a paint formulation, these remain particles. In contrast to dyes, a dye will dissolve in, for instance, a plastic or in a coating. Pigments are more expensive, but they are much more stable against weathering. They retain the colors over a longer time. And of course, they are the safer alternative compared to dyes, because a particle is much less prone to migration than a molecule. And so let's look at solubility of these materials. And here you see some typical photographs, and most of them are colorless. And that's, of course, the nice thing about pigments. You immediately see if something happens. So for these two materials here, clearly something happens. And also for this one, something has happened. And this is highlighted here in the percent dissolution in a static test. It's a lysosomal simulant in a static test. For two materials, we have a significant dissolution, which is 2% or 18% for the other one. And these two happen to be both metal lake pigments. For the others, the relatively low dissolution also has to be confirmed then by dynamic testing. So this is a typical example of a dynamic or flow through testing for a really insoluble material. So note that this here is 95%, this is 100%. So you just don't see any dissolution. That specific material here is a diketopyrrolopyrrole. But for the one material that already was identified as slightly soluble in the static test, you also see a time-dependent dissolution in the dynamic test. So that confirms by a tier 2 method that this material is really different from the others. It was a candidate for our grouping, but at least in that parameter, it is different. Now the question is how different, and is that already beyond the acceptable range? But for that, we also need to look at other properties. One of the properties that are mandated by the IATA is reactivity. And here we are using the standardized electron paramagnetic resonance, which is less sensitive than the FRAS assay that we would otherwise prefer. But the big advantage here of EPR is that it is completely insensitive to color. It only looks at radicals, whereas most of the other abiotic assays use some colorimetric readout, and that's also the case for FRAS. And color is an issue if you work with pigments. So two materials here have a statistically significant reactivity. All of the others remain on the order of the blank control. So for these two, there seems to be something happening. As it turns out, one of them is the same material that also was identified as partially dissolving in a different pH condition, but still it again is something like an outlier, and one of the copper phthalocyanins. If we now, it shouldn't be here, why is it here? If we now go to the similarity analysis, because we are looking here at chemically different species, we have first started with a chemical similarity analysis, which is clearly beyond the Gracious framework. It's not requested in the framework, but Nina had those tools available and they work. So here we also use not a triangular similarity analysis, but that's something that Nina has also introduced yesterday in the similarity session. She clusters or rearranges the sorting of the materials according to their similarity, which only confirms what we knew before, but it's good to see that these materials are classes of pigments. So you see that this algorithm confirms the similarity of all the DPP-based pigments. Cosmoray also is a decayed pyrroloporone material. It confirms the relatively lower, but still obvious similarity of the two parylene materials. And then for some reason, it arranges the titanium dioxide, zinc oxide, and copper oxide reference materials into one class here. It does recognize all the diarylite pigments as one relatively similar material, but it's interesting to see that the copper phthalocyanine remains solo, and its chlorinated analog, the copper phthalohalogenated material, which is green then, is only a little similar. So you see that orange color here. So it's not even sorted together with its analog because it really is significantly different. And again, the two metal lakes are sorted together. So this will also then be now our basis to assess how relevant all the other findings are, because we want to understand to what extent findings are related to chemical structure or to nanoform structure. Looking at dissolution, we have this very large green area here. And it's deep green, which means perfect similarity, because we are using the concept of a biologically relevant range, which means we're not interested if one DPP has a half-time of 700 days and the other one of 500 days. That is very slow dissolution. And we say that this is then identical for the purpose of similarity assessment. And that's actually the finding for a large number of these pigments. So all of them that are similar to each other here are materials that are very slowly dissolving below the thresholds. Two others, parylenes here, also are very closely related to each other. But all of the materials, as you can see here by the reddish colors, are very different from something that does dissolve, like zinc oxide. One material that has an intermediate dissolution rate is yellow, and all this makes sense. Looking at the inflammation in macrophages, here we selected one of the readouts, the LOEC of the TNF-alpha production. We have, again, positive controls which show what they should do and which is a significant inflammation potential. So we see that from DQ12, and we also see it from zinc oxide. We also see some reactivity or some inflammation with the copper phthalocyanine nano form, which is much less pronounced with the halogenated form. And again, we have this big group of materials, and now I'm really starting to call it a group, where also the inflammation is below thresholds, which means that even at the highest dose tested, we do not see an increase of the TNF-alpha production. We can now correlate those findings to the chemical similarity. So at the bottom, you see the chemical similarity, and each dot represents a pair of materials that is analyzed by two axes or by two dimensions. They are analyzed by their chemical similarity and by their similarity of reactivity. This means that for all these materials, we have a high similarity by chemical similarity, which is predictive for a high similarity of reactivity. And except for this one outlier, that's also the case for the dissolution. So that up to a certain chemical similarity, that is sufficient to predict the similarity in the dissolution. That's not so easy for inflammation. There are many more dots here where a certain similarity in the chemical structural analysis still allows for differences in the information. So that only means that our IATA works, because if everything was predictable by chemical similarity, we wouldn't need an IATA. So it makes sense to have that separate decision node on inflammation, because it does provide an additional information that we don't have by PhysChem alone. Looking now at the tier 3 in vivo results, here you see the different endpoints that Lan and team have analyzed, and all of this is by the short-term inhalation screening, which means 5 days of exposure via inhalation on rats, and then the final evaluation at day 28. So there's a 3-week recovery period. You also see the exposure concentrations, which are high. 30 milligrams per cubic meter is a very high concentration. For some, we also had different a dose range, but for some, we were guessing that they would have low toxicity, and so we were testing a single high dose. Taken together and also compared to reference materials, it's qualitatively similar in this short-term test to cerium dioxide or to titanium dioxide, which were again analyzed in the same test. But also within this entire group, the qualitative results are similar. And I don't know why this slide was double in the presentation, but here is the quantitative similarity now. So the potency of materials analyzed by different approaches. You have the NOAC here, and then Lan performed a benchmark concentration approach where titania and ceria range a bit lower than the pigments where we have the dose response and we analyze the BMC. For the other materials here, we have a NOAC that coincides with the highest dose tested. There's one material, and maybe you remember that this pigment blue 15.1 copper phthalocyanine nano was found to have an effect in the macrophage inflammation, which is not confirmed in vivo. So this is something like a false positive of our alternative techniques. I think it's not a false finding of the IATA or of our similarity analysis. It is a false positive of the alternative approaches, because in vivo it is just as low reactive as the other materials. So based on the potency, we don't have an indication that would contradict the grouping of the organic pigments, with the exception of those that dissolve and so behave differently from the others. To conclude, all decision nodes are applicable to pigments, with the caveat that some colorimetric methods may have interferences. We struggled a bit when we put all this together, how we would assess the different readouts of the macrophage assay. And beyond what I've shown you, we have also performed the same similarity analysis for the other readouts. So looking at LDH or glucuronidase, which lacks guidance on how to proceed here. We see that in the Euclidean distance with the Yeo-Johnson data transformation, a distance of 1.5 is what we find for those materials where we do have acceptable in vivo similarity. So when the tier 1 comes out at 1.5 distance, that's again a rule of thumb that we still need to consolidate, but it's a good example. This seems to be acceptable as similarity, compared to a distance of round about 6 for the reference material pairs. We did restrict our similarity analysis to the biologically relevant range, and that turned out to be very important, because otherwise we would interpret noise, or we would interpret irrelevant differences, such as what I mentioned, the difference between 500 and 700 days halftime. so the IATA was applicable. We had to exclude 2 candidate nanoforms from the group, and they turn out to be the metal lake pigments, so they cannot be grouped with others. 2 more, one of them being the copper phthalocyan nano, had to be escalated from tier 1 to tier 3, and then we had the evidence to group them. Otherwise, we would have had to exclude them. On a different note, the chemical similarity was rather well predictive for the similarity of reactivity and dissolution, and to some extent also, what I didn't show, to multidimensional similarity. Yeah, and with that, thank you.
Okay, thanks, Wendell, for the excellent presentation. Currently, I see no questions in the chat, but still, I would like to give the audience the possibility. Maybe you can stop sharing the slide, and so that we can see the participants. Maybe there are direct questions to Wendell before we move to the overall panel discussion.
Or to Nina.
Yeah, maybe also to Nina. I think Vicky did you raise your hands freshly, or is it still from previous session?
Yeah, it's a fresh one. Sorry, Wendell, but I missed this in your presentation, but in your discussion at the end, you said something about when you were comparing the results of the NR838 3 macrophage assay, you had some problems with understanding or interpreting the readout of the or assessing the readout. I wasn't quite sure what you meant.
The issue is that within the same assay, you can use different reporters. And here I presented the results on the TNF alpha, but we could have done the same on the LDH production or on ROS production. The same applies to many other cell cultures. I'm not sure if we have good guidance on how many of them need to be evaluated, or if we can just pick one that we think is sensitive to the specific group of nanoforms.
Well, all of those endpoints are measuring something quite different. So when the IATAs, and Fiona and Andrea can correct me because they're more familiar with this, they do specify endpoints related to cytotoxicity, endpoints related to inflammation, endpoints related to genotoxicity, etc. So each of those endpoints that you just mentioned would map onto those different things. So I think you can't lump them all together into one analysis. Yes, they've come from the same experiment, but they're measures of completely different things. There will be some relationships between them. For example, if you kill all of the cells in the culture, they won't be able to make TNF alpha. So you need to make sure you're looking at analysis of data with sublethal concentrations, things like that. But maybe we can just have a look at which IATA you were looking at, to see where the guidance was missing. If it's present in another IATA or it's present somewhere else, we make sure the links are clearer.
Let's do that. And of course, this was the inhalation IATA for slowly or very slowly dissolving materials. So only one decision note refers to the inflammation potential under in vitro conditions.
Yeah. Okay.
Wendell, I had one quick question. You mentioned the false positive from the alternative testing on the in vitro. Can you link that to any specific physicochemical property, like the reactivity or something like that? And is there something that's a physicochemical property that might lead more to a false positive in vitro for other materials going forward?
Yeah, that we would like to understand better. The specific material is the copper phthalocyanine, which consists of 90% organic and 10% copper. The copper is not bioavailable from the actual particle, but we did find in the meantime that there are some copper impurities. So over the first few hours, we, again, in vitro, we see a release of some copper, which then saturates and nothing more happens. Maybe, we don't know, maybe the in vivo test is less sensitive to those low concentrations of that copper impurity, which is a remainder from the synthesis, than the cell culture and abiotic reactivity testing. We do know that the reactivity test is sensitive to copper ions. So maybe that's the point.
Yeah, that's very interesting, because we're doing some copper in vitro with copper welding fume in vivo and stuff like that, and we're seeing some effects in vitro with the copper specific maybe versus what we may see in vivo. That's interesting.
Okay, so then I think it's time to come to the final overall discussion. I would like to thank all the speakers again for their excellent presentation, and also all the audience for the very lively discussion. Before going to the final overall discussion, just let me briefly remind you of all the case studies that we had, because today we only had the possibility to show you some of them. And you see there were quite some more on the inhalation route, having carbon black materials, silica. We had one covering the oral route, again with silica, and we had two other internal case studies on the environmental aspects, just to have the complete picture again. And currently we are preparing recordings, and the idea would be to make also the other case studies available alongside with the recordings of this workshop. So hopefully soon you will receive more information. And just to complete the picture on the external case studies, because I was quite short in the beginning, also BFR led a case study on multi-wall carbon nanotube and the inhalation route of exposure. We had another case study from the National Institute of Health in Portugal, another one from a consultancy, Blue Rock, and then one from the Finnish Institute of Occupational Health along with Grupo Antolin. And also here we offer them a possibility to provide more recordings, and we will see what will be the outcome here. So yeah, hopefully soon we can provide even more information. Before we go to the final overall panel discussion, where we also prepared a couple of questions to discuss with you, I have another voting, and I hope you don't mind. This is now a new number in Mentimeter, and we are pretty much aware, this is the number in the chat, but also you see it in the screen, that of course you only had a snapshot view on what we have done in Gracious and no in-depth understanding, but maybe justly as a roughly gut feeling from what you maybe have seen yesterday and also today, how would you overall evaluate the framework from your perspective, even so you don't know every detail, the hypotheses and the yatas that have been presented? Not all of them have been presented, the case studies in particular that you heard today, and maybe also partially similarity assessment, just as a gut feeling. Yeah, if you like to share your opinion, it would be nice if you go to Mentimeter again, so www.menti.com, and use now the fresh code. And wow, the picture is really cool. We see overall, yeah, people are very positive about what they heard yesterday and today. Now it's a bit coming down, but I think still it's a very excellent picture so far. I will wait just a few more minutes before I open the slide with the final discussion questions. Maybe you can still vote here. So the voting is open, yeah. And in between, I can already share now the slides with the question. So the first questions would be, in several of these case studies, we have seen issues with data gaps and data availability. So in case available data is limited, would you consider comparison across different assays eligible? because we, of course, suggest and prefer that for a single decision node, the user should take data from the very same assay to make it really comparable. But in case this is not available, would you think that this is justifiable, and if so, under which conditions? And do you agree that benchmarks, which we suggest to always include, do you agree that this should be included to increase the comparability? Vicky, you are raising your hand already.
Yeah, so in the guidance document, we were quite clear, and that we said that for an individual decision node, you should always stick to exactly the same SOP for all of the nanoforms within your group. But actually yesterday I was reading, and I don't remember exactly what I was reading, but I was reading one document from the project, and there was a suggestion that actually for regulatory purposes, yes, you absolutely must use the same SOP across the nanoforms within a group for a specific decision node. But if you were going for an early innovation stage, so in the safe by design approach, you could be much more flexible about that, and that you might be willing in that instance to take data from different sources, different SOPs, providing that you could understand it and you could, understand some rationale behind it. So I think it might depend upon the purpose of the grouping.
I certainly would tend to agree, yeah. Do you think that the inclusion of benchmark materials improve the comparability of the results then in that case, to make that maybe a little bit more justifiable?
Yeah, especially if you can have exactly the same benchmarks in the different assays. So if you measured, let's take Vendel's example earlier on. If you measured surface reactivity using EPR and surface reactivity for other materials using DCFH, but if you have the same benchmark materials in those two different studies, then that would give you a bit more confidence about making that. But you definitely couldn't do it, I don't think, in a regulatory application.
Okay, any other opinions on that before I go to the next question? And if you like, please also share your opinion in the chat. Anybody else would like to speak on this? If not, I'm happy to go to the next slide and share the next question. In a couple of the case studies, actually, not so much in what we presented today, but in a couple of the case study, we also have seen issues coming up with respect to the dose metrics. In particular, let's say inflammation or reactivity. If we compare different nanoforms, let's say on a mass-based dose, we may see differences that are not apparent on a surface-based dose anymore. I know this issue is an old one and has been discussed intensely, in particular for in vitro nanotoxicology. So maybe you have some views on that. How you, because for a grouping you need to make a decision on a similarity, and you compare different nanoforms, and maybe you have any views how finally a decision should be made and justified, because in the end it's either the nanoforms are similar or they are dissimilar. I will check the chat. Yeah, of course, Willy had some suggestion on the dose metrics. It's a very good response by Vicky. Any other opinions on this? Maybe it's a trivial one because it has been intensively discussed, but really how to implement that for the grouping and for the decision notes. Maybe Willy, would you like to share again your views on this? Maybe not. It's okay. We go, yeah.
Andrea, I sometimes think that the surface area issue, so surface area metric is an important one, and it kind of has a number of connotations. So for dissolution, the rate of dissolution is going to be related to the surface area per unit mass, but also surface reactivity as well. So I think,
Yeah.
The surface area metric needs some careful consideration. I think you need to first of all ascertain whether you're looking at something that's very slowly dissolving or something which is rather quickly dissolving, and then you can make your consideration of dose metric and how it influences your data interpretation based upon that, perhaps.
And now Willy would like to speak, and then Wendell.
Yeah, I apologize for slowly being able to unmute. But I basically agree with what Vicky says. What we found is that indeed surface area is a key parameter, and that is reflected in things like even the size being important in the examples that I've shown. And as I already said, it's also reflected in the fact that when you take differently shaped particles, the surface area, the volume, or any related property, any related dose metric, that is best describing the actual dose. So that's in line with what Vicky said, I think.
We have two more, Wendell and then Eric.
Of course, normalizing effects to surface area works in many cases, especially for the relatively simple particles that we have been looking at here, which are the most relevant particles. It's the ones that that are constituting the big dossiers of nanoforms, but we don't know how to handle accessible surface areas for pores of varying diameters or for materials that have inner surfaces. So for that, I think we will continue to juggle both mass and surface area metrics.
We had an example in the oral case study where two mesoporous silica were included, and as far as I remember, they indeed were very much different, right?
There we had contributions from both the inner and the external surface. That's one of the cases that is relevant here, absolutely.
Okay, so very good points. I completely agree with this dissolution and maybe also surface reactivity and also biological accessible surfaces is key. Eric, you would like to add?
Yeah, just to put a small caveat there, I think if you can already see on a mass base that something is really quickly dissolving, I don't think you have to look into the details of the surface area, and similar maybe with some reactivity studies, but clearly in the more uncertain parts of your distribution of dissolution rates or whatever endpoint, it might become more important to have a critical look at other metrics.
Yeah, thanks. And also, yeah, we see it also for more biological. So also inflammation was another decision node where we have seen differences in some of the case study. Okay, let's move on. Yeah, there was also some comments in the chat by Neil, for instance, on the similarity approaches. So they have been presented yesterday and partially they have been included also today. How useful do you consider these approaches that have been tested by Gracious, and maybe from what you heard, do you consider some of them maybe more fit for purpose? Wendell already did this very nicely in his talk yesterday, where basically the conclusion from Gracious is that for, let's say, sound decision making, a pairwise comparison should be made. But maybe it's worthwhile to have a little discussion also on these similarity approaches in the context of the case studies. Is there anybody who would like to share his or her opinion? If not, I could ask Nina and Wendell, because they are the two experts on the different similarity tools. And I know that Wendell already answered this question from the perspective of Gracious, because we have some conclusion here. Wendell, maybe you would like to repeat from what you said yesterday in your presentation.
Sure. We did not evaluate all algorithms that are around. We did evaluate 4, in detail, and we did find that they are mutually consistent. It's important to remember always that the actual distances that are measured by these algorithms are not the same ones. So if you apply a similarity analysis by one algorithm for one purpose, you can still apply a different algorithm for another purpose. But we did find that the Euclidean distance works if you ensure data transformation, and Nina can say more on that. She had an excellent slide on it yesterday also. And we did find consistent approaches by the X-fold, which also matches what's done in the ESSETOC Nano app, and by the ordered weighted average or Arcosinus approach from Alex, and the Bayesian statistical approach from Georgia. Always with some caveats. Using reference materials is always a good idea, and data transformation is important. Nina, you are really the mathematical expert here.
Yeah, thanks for the chance of commenting. I'd like to say that chemical similarity is a very well established field for the last couple of decades, and they're very widely used in screening, in drug design. So this is nothing new from all these methods, including the chemical similarity. They're very well known, and there are hundreds of such methods. And the caveat is because similarity is not something absolute, so there is no easy answer. Use this and you're done. You basically need to see what works in your use case and make sense of what you see. And also I'd like to say that similarity assessment in the way that is being used in Gracious is completely unsupervised method, which means that there is no guarantee that you find causal correlations. So if you find that something is working, one similarity predicts another, this might, it's not necessarily a causal relationship. So use it with care.
Okay, thanks, Nina. Eric, you raised your hand.
Yeah, thanks. More or less echoing a comment by Neil in the chat. Although Nina rightfully indicates that it's been around for quite some time now, the similarity assessments, still it could be new to some people, and we might need to have a look, because Wendell presented, for instance, 4 different methods yesterday, but choosing one of them if you want to, or do you have to do all 4, or find how to find the best one? Maybe some further guidance there would be helpful, and maybe something as Neil calls it, a similarity for dummies type of document would be helpful there.
Yeah, thank you. Before closing the event, for sure, I also would like to give the possibility to the audience to raise other questions. Now, having heard all the case study, maybe you have some questions to refer to all of them, or maybe you have a specific comment or a suggestion. Is there anybody who would like to share some thoughts or has some question? Meanwhile, I will share again the outcome from the voting. So you see what is the current picture in the Mentimeter. I think overall the responses are very positive. And I have a second question. If maybe you have any suggestions from what you heard today that could improve maybe some of the case studies, decision notes, IATAs, or also maybe enhance regulatory acceptance. It's still the same code. You can type anything that comes to your mind. It is an open question answer. Of course, more case studies for sure. We all agree on that. So this is really, really important. Well, you can type in whatever comes to your mind. I will stop sharing whatever you think is relevant, please share with us. And maybe we can discuss a bit on the regulatory acceptance also. You have some views on that? Would you, because also we have many participants here who work in small or medium or large enterprises having to deal with REACH, and also one case study has been presented from a consortium that works under REACH. What do you think about regulatory readiness, let's call it like that?
Andrea, maybe I can help a little bit with a slightly more simple question. So when we go and speak to the European Commission project officer, she is always accompanied by a specialist, a scientific reviewer. And our particular scientific reviewer has been excellent. And there is one question that she brings up time and time again. And that's, how have we interacted with SMEs and how have we tried to work with SMEs? And my gut feeling is that the framework is too complicated for most SMEs to use themselves if they were an SME that manufactured nanomaterials. And that it's more likely to be a consultant of the type of Blue Frog or Jordas or Arch Consulting that would do that work on behalf of those SMEs. But that's just my gut instinct, and I'm interested to hear what other people think about that.
Okay, Wendel, you raised your hand.
Well, Vicky is right. Even within a large company like BASF, this framework is too complicated for most run-of-the-mill product stewards. So people who are responsible for a certain part of the portfolio and who only deal with nanoform issues every few months, they will not go into the depth of this framework. So even in our company, it's a handful of people that can handle it, which in a sense have the same purpose as a consultant would have for any other approach. We are somehow the internal consultants. And that, I think, is okay, because we don't have the scientific evidence to simplify the framework to something that consists of just two simple questions. That's not there. But the other challenge is that the acceptability of grouping approaches is low in dossier evaluation. And if we don't create more precedence cases, and the work by the Zinc Consortium is one of the examples where large numbers generate evidence that grouping can work, we also won't get the more complicated cases done. So precedence is missing. It's a real issue.
I certainly agree to this view, and also for your arguing against simplification of the framework, because currently we have no evidence. But then the question is, how can we enhance even the applicability, let's say, in case studies or in for especially small and medium enterprises? There is Frederick. Fred, you raised your hand.
Yes, I'd just like to follow up that, having been involved with the EPA and the FDA, I have a feeling that the discussion today is on grouping of nanoforms, and everyone was doing that very well. But when you go to the regulator, you will probably be relating this grouping of nanoforms to the one you selected to be representative of the group for refined testing or extensive testing. Or you'll be making a decision as to, will you use the ends of the group if you're doing pairwise, or will you use a single entity? So for silicas, you may have a group by surface areas, but you did all your work on the 200 meters squared per gram, and you're going to have to demonstrate that. So the regulators may not be asked the question on how they will use the grouping. They're being asked, did you like our group? And maybe the response is, well, what are you going to use that group for in a submission? So I see a slight difference in perspective there.
So actually, Fred, I'm not sure there is. I think we probably just haven't demonstrated in the last couple of days that next step. We haven't really focused on read across, for example, in any of the presentations that we've given. So actually in Ralph's presentation yesterday, and it may probably most people missed it, but when he presented his similarity assessment, he did it slightly different to the way that Wendell and Nina have done it. So Wendell and Nina have always presented their similarity assessment where you compare every nanoform with every nanoform and your sources all in together. But when Ralph presented it, he presented the similarity compared to a single substance. And that single substance could be a nanoform, it could be a non-nanoform, but it's your source, usually your source material. And so all his comparisons were to that. So that could be your 200 meters squared per, or whatever your example was there. So in that case, your output would allow you to see which of the nanoforms and substances in that group were sufficiently similar to that material that you have all the data for, that is your source, to say that they can be grouped together, and therefore you could conduct read across from that one material where you have all the data to the other ones where you're lacking it. And I think we haven't described that well enough, perhaps in the last couple of days. And perhaps Vicky, it addresses that.
And Vicky, I was just making that comment. Is that how you phrased it to the people you were calling on at the regulators? Did we connect it to the source? Maybe your examples on that day were more the general grouping and not the specific to the source. I would assume they would respond more thoroughly, or shall we say, think about it more, if they saw an example that they would have to be making a decision about, as opposed to a general grouping. That's a nice group, but not being asked a specific question.
So maybe Andrea and Fiona can comment on this, because the multi-walled carbon nanotube case studies, they've done exactly that. So for example, the Mitsui 7 is often the source material that the other materials are therefore compared to. I mean, Andrea, do you want to add to that?
Well, I would just echo what has been said. I mean, all of these different issues are important for regulatory acceptance. So the first important question, how do you justify your grouping? What is your hypothesis? What is the evidence that, so this is the grouping itself. But once you have established a group, it is a very important decision. You use data to justify the grouping, but then for read across, which is typically, let's say, the outcome in a regulatory setting, you need to identify a source material. And as Vicky explained, we discussed that. And the case studies that we have conducted are case studies. However, we had, I think, very fruitful discussion with regulatory bodies such as ECHA and EFSA. And I think they very much appreciate the work that has been done in GRACIOS, and also the guidance document and the guidance in a nutshell will be or is already shared with them, and for sure we will also receive some more detailed feedback then on the guidance, and we will see how well did we cover all these issues in our guidance document. Vicky, that was not precisely what you asked me to answer, but I felt that this is also worthwhile to emphasize. So for sure we get more feedback from the ECHA and EFSA side.
And in fact, we do have an ECHA representative if anybody wants to speak up on the call. I'm not going to name names. And also, Erin, I don't know if you considered the read across. I think you did in your case study as well for NIOSH.
Yeah, I mean, we built our study around the reference material of Mitsui 7, and that way we could evaluate all the materials. And I think the way we designed our study, the goal was to go from one end of the spectrum to the other, so that we could theoretically, at the end of the day, once we got all of our data together, if the study was well enough designed, could we take a new and emerging material, a brand new multi-wall, and could we boil it down to the few key factors that were important? In our case, we want to go all the way back to dimensional characteristics alone. Can we do a dimensional profile of bundled agglomeration with length and diameter binning? And can we predict where this material falls in terms of our categories of toxicity? And honestly, we're actually in the process of, we have a high volume new material that we're doing the case study on to go into where we have our 9 materials. We're going to take just the physicochemical dimensions and we're going to do a predictive nature of it to see this is what we should expect in terms of inflammation, in terms of pathology and things like that. And then we're actually going to do the study. So independently, we're going to have our modeler tell us what their predictions are for the material. And then we're actually going to do the validation study to see where it falls. So in terms of my perspective on this thought is as we develop more and more data on the toxicology side, we can further and further narrow down what industry would need to provide to have sort of a predictive approach of what this toxicity of this material would be. I think you asked the question in one of the previous calls, did we need inflammasome or frustrated phagocytosis to accurately group the materials? It was great in the beginning to have this complementary feedback to confirm our grouping, but really we're working our way all the way back to dimensional characteristics where in the case of maybe the high aspect ratio materials, we might not need all of the follow-on in vitro and in vivo studies if we have a well-balanced, detailed toxicology studies as the basis for developing where we go forward.
Hello, Aaron. This is Fred Classic, also from the US. Has the EPA accepted the results of your work in the sense of the SNR on carbon nanotubes? I think 3 companies submitted the 90-day inhalation studies and then it stopped. I never heard any further from it, but have you made progress in the sense of EPA acceptance, which I believe is what Andrea's original question started with, or acceptance by regulators. So has your work been accepted by the EPA?
I don't know that it's been accepted as of yet, but they have been introduced to it. So when the work first came out and we published the paper in December 2020 with the beginnings of hypothesizing that, we presented on the USNNI call of all the federal partners, of which EPA was on board, and we did have a discussion of how this will affect grouping and determining what nanomaterial toxicity is moving forward. So there has been an initial discussion. We're going to have these next 2 papers. During this meeting, I actually got a call that one of them's been cleared so we can submit it to a journal. So we're going to have 2 more papers come out. But yes, EPA is part of those calls and part of the NNI, and other people had that discussion of the impact of that type of approach moving forward for new materials. I don't want to be oversimplified, but theoretically, if everything aligned, we could go from demanding a 90-day inhalation study to $5,000 worth of extensive dimensional characteristics and have presumably relative confidence in the same outcome. I mean, that would be the end goal to make this worthwhile.
Great, thank you very much.
Thanks, Aaron, for sharing these very detailed additional insights. I think that was very, very useful. Also, the discussion that was initiated by Fred and these answers. So thanks a lot for all these detailed insights. And having a look at the time, I think we are already coming to the end of the meeting. Before we really end, just let me, for the last time, share with you the outcome. So here, just to show you, we really received a lot of input that for sure we will read with more time. So I will leave the Menti open for a few more minutes even after this meeting. So if you have any suggestion, you can still use this code. You see there is really a couple of input already in, and I will also share with the Gracious team, of course, maybe some of that can be considered in future projects that were already mentioned. So I'm sure you already heard yesterday that we have 3 projects that already started: Harmless, Sunshine, and Diagonal. And indeed, we have an ambassador meeting coming up up tomorrow, where we will discuss which parts of Gracious can be relevant to be taken up in this new project and to be considered for, let's say, more advanced materials. So having said all of that, I don't want to have the last word because I'm not the coordinator. I thank again everybody for this wonderful workshop, and I will hand over now to Vicky for a final word to close today's event. Thank you.
Thank you, Andrea. I think that's a really useful point to finish on, that there will be the meeting tomorrow. So while this is the end of the Gracious project, at the end of this month, it won't be the end of the activities relating to grouping and read across and the collaborations that we've established here. Many of us will continue to work on this in under the guise of multi-component nanomaterials. So we look forward to doing that, but also the OECD will take on this activity as part of their grouping and read across for nanomaterials in the OECD Working Party on Manufactured Nanomaterials. And the US, in fact, Fred, will be in the co-lead with that, with myself representing the US. So I think hopefully that will provide some continued momentum to this work in this area. So I would really like to thank everyone for taking part in the really stimulating discussion, for your inputs today, for the feedback that we've provided. I've made a list, Andrea, of actions or ideas of things to discuss to come out of today, some of which can be addressed by the Gracious Consortium, but some of them I think we can pass on to Sunshine, Diagonal and Harmless. And so I think that's been really, really worthwhile discussion. So thank you to Andrea for all the huge amount of effort that she's put into coordinating the case studies. Thank you to all the people who conducted case studies, because it's been a huge amount of work, as you can see from those presented today, often with no budget provided by the Gracious Consortium. So we're very, very grateful for that. We'll look forward to seeing some of you tomorrow afternoon. And as soon as the final guidance document is available, we'll let you know. The draft version with just missing a few bits and pieces is already online, so you can already download that from the Gracious website now, but we will let you know when the final version's available. So thank you, Andrea, and thank you everyone, and have a good evening.
Thanks, Vicky, and goodbye to everyone.